Hello and welcome back. Today we're going to be taking a look at how we find the area underneath a path in 3D. We call this a line integral. So many times we want to find the area under a curve, such as the graph here below. Right? We have this line, we want to find the area underneath here. Well, in 2 dimensions this is easy. Last year in calculus we talked about if I have a function and I want to find the area underneath that, I can just integrate from a to b, and that's going to give us f of x dx. However, this year we have been dealing with functions that are in 3 dimensions. So suppose we want to find the area under a curved path. So when we look at this image, we want to find the area underneath this curved path. To do this, that's where we're going to be using something called a line integral. Now, for me, it's helpful to think of the area as if we're looking at a curtain or a wall being projected to the xy plane and intersecting the function. Today, we're going to discuss how we find that area. So, in order to evaluate a line integral, now again, a line integral is simply put, is the area under a path. Remember, and we talked about paths earlier this year. Check out my earlier videos if you need to. We are going to need to convert these into parametric form. This is going to make it way easier to solve, and we'll talk a little bit more about why that is later on. So let's go ahead and review how to convert a parametric function. So we're given the parametric, we want to, find the parametric equation of the line with the following 2 points. So we have these 2 points in 3 space, and we want to find the equation of this line. Well, in function notation, it's much harder to write this in terms of x and y. We had to use our symmetric equations. You might recall those earlier. It's easier to write the equation of a line with parametrics. So there's a couple ways we can do this. One, we can just look at, write it as a vector first. Remember, a vector equation of a line is going to be your initial starting point, a, b, c. Add to that some variable t, that's our independent variable, and you get the change in x, change in y, and the change in z. So I can write my vector equation as x, y, z equals, this is just 1, 2, negative 1, plus t. My x's are increasing by 1, so my change in x is 1. If I start a and I go to b, that's basically what we're doing. If I go from 2 to negative 3, we're decreasing by 5 for my y values, and my z values is just going to be, I'm going from negative 1 to 0, so we're increasing it by 1. From here, I can write my parametric. And x is going to be 1 plus t, y would be 2 minus 5t, and our z is going to be negative 1, just match up the like parts, that's all we're doing, plus t. So there's my parametrics equations for this line. Now remember, this line, these would go on forever unless we have a restriction. And we do have a restriction. Because remember, we're starting at point A. We want to end at point B. So we have a domain, we're obviously going to have a domain restriction. And since we're in parametrics, our domain restriction will be in terms of t. So to find the domain, we're looking for that change in the t values. So how do I find the change in the t values from when I start here and I end here? Well, all these should have the same t values because they all start, all the x's, all the y's, all the z's start and end at the same point. So all I need to do is just pick one of these letters to work with. I'll look at the x's. You can use the y's or the z's the same way. Well, the x's at point A, this is where I'm starting. At point A, my x equation is just 1 plus t. Well, my x coordinate at A is 1. Therefore, I'm starting at t equals 0, because remember, that's where we're starting. I'm ending at B. Well, again, I'm going to get this 1 plus t. Well, where does at point B my x value is 2? So my x value starts at 1 and ends at 2. And that's going to give us t equals 1. So we now know our change in t. That it's going to be this parametric equation such that t is between 0 and 1. So this is our parametric equation. And we can do this for all sorts of paths. Let's go ahead and find the parametric equations of the following path C. Now C consists of 3 line segments, C1, C2, C3. So C, this is going to be our total path right here. So we're starting at C1, 0, 0, 0, and we're heading towards 0, 2, 0. So that's C1. C2 then starts at 2, 0, 2, 0, ends at 1, 2, 1, 0, and then C3 is the path going straight up to 1, 2, 1. So we're going to have 3 different parametric equations right here. So let's work with C1 first. C1 starts at 0, 0, 0. It's a vector, so direction is important, and we're heading to 0, 2, 0. Now I could write this as a vector, but I'm pretty confident in my abilities right now to write this as a parametric. Because my vector, I'm only looking at the the corresponding x parts anyways. So my first x value right here was 1 plus 1t. So here I'm starting at 0 plus, well, what's my change in x's? I'm going from 0, I'm ending up at 0. So that's plus 0t. So my x value is 0, always going to be 0. My y starts at 0, but my y is increasing by 2, so it goes plus 2t. And that's just 2t right there. My z's, starting at 0, I'm not increasing it, so it's again plus 0t, and that's just 0 right there. And it should make sense. The only for C1, my path 1, the only variables changing is y. My x's and z's remain the same. So my x and z's here, there's 0 change in there. Now I do need to find my domain, which is my change in t. So t is going to go from, now again, I have to pick a variable. The only one with the t this time is y. So I'm going to use my y's. So for my y's, my starting point was 0. So 2t would be 0. So that's easy. T is 0. My endpoint y is 2. So we go 2t equals 2. T equals 1. That's what we're looking to. And 1. And so here's our parametric equation for C1. So let's take a look at path 2, C2. Path 2 starts at 0, 2, 0 and goes to 1, 2, 0. So I can look at my x's. Now take a look here. This is going to become 0, but I'm increasing it by 1. So we have 0 plus 1t. So that's just t. My y as a parametric starts at 2, but I'm not increasing it at all, so plus 0t, so that's 2. My z starting at 0, again, I'm not increasing by anything, 0t, and that's 0. So there's my parametric equation. So let's go ahead and get our domain here. And that's my change in t. Again, the only one really changing is x at this point. So I'm going to use my x's. So my t, my t starts at, this is where it starts. This is easy this time. T is just starting at 0. And where does t end? And it ends at 1. So this goes from 0 to 1. And here is, again, our parametric equation. C3, PO, copyright. Right, so we're going to start here at 1, 2, 0 and heads up to 1, 2, 1. To get my x's, I'm starting at 1, but I'm not increasing my x's, so plus 0t, and that's just going to be 1. My y's, starting at 2, I'm not increasing my y's any, so that's plus 0t, and that's just going to be 2. This time my z's, though, start at 0, but I'm increasing it by 1t. That's like my slope for the z's, and that's just going to be t. To get my domain, again, that's my change in t. but this time we're going to use the z's. So I'm starting at t equals 0, and I'm ending at t equals 1. So my domain on t goes from 0 to 1. And here we have our parametric equation. So remember, when you write a parametric equation, they can go on forever. We have to restrict the domain to make sure that we're only on the part that's going to be in our path. And that's where we have to talk about those domain restrictions there. But remember, the domain restrictions in the parametric are in terms of t, not x or y or z, just in terms of t. All right, I hope you enjoyed the video. Go to video number 2, and we're going to take a look at what a line integral actually is. See you then.